Okay, so in this video, let's talk about chapter 7, trigonometric functions. Trigonometric functions. The first section is angles and their measures. Angles and their measure. So the trigonometric functions have input angles. So we just get the basic information, knowledge about the angles. What is an angle? Angle is formed by two half line. Half line, you have a vertex, you have a point, you have a direction. This is half line. And this point is called a vertex. Okay, so this is a half line or a ray. Half line or ray. A half line or ray with a vertex with a direction. If two rays share the same vertex, then they form an angle. They form an angle. And once you have two rays, one ray is called the initial side. The other is called the terminal side. Okay, you have initial, have terminal. And for example, when you have this, you don't have to draw this arrow, just two rays. When you have this, if you draw the angle, this way, this is initial. This is terminal. Or you consider this one as initial, this one is a terminal. It's up to you so far. There's no requirement. Or maybe you have initial terminal, but you consider this one. Okay, so the difference between the last two examples is that this one is a clockwise. We say clockwise orientation, like how the angle is formed when you swap the initial side to terminal side. It is clockwise, and this one is counterclockwise. In angle study, in the trigonometric study, the clockwise we consider the angle to be negative. To the counterclockwise orientation, we consider the angle to be positive. Okay, so we do have positive angle, negative angle, but those positive, negative just means the direction, the rotation direction. Okay, it's a rotation direction. And when we have angles, we prefer use alpha, beta, gamma, or theta. It's just a convention. It's not the law, right? It's not the law. It's just convention. For many cases, we like the Greek letter to represent the angles. Okay, but if we place the angle in this way, it will be so random. It's not easy for us to study. So we are going to place them in the standard position. So an angle theta is said to be in standard position if its vertex is at the origin and its initial side coincides with positive x-axis. Okay, so what is that? So you place the initial side along the positive x-axis, and you just determine the terminal side. This is theta because it's counterclockwise, it's positive, or maybe you have the initial side and the terminal side is clockwise, it's negative. Okay? Keep in mind, counterclockwise positive, clockwise negative. So this is the angle and the standard position. So the initial side is always the positive x-axis. Okay. So if your angle, the terminal side, is not does not coincide with coordinate axis, okay? So if the terminal side lies either in a quadrant, lies in a quadrant then we call theta is said theta is said to lie in the quadrant. For example, like this. This theta is this theta lie in the quadrant, is in the quadrant. Or the terminal side lies on coordinate axis, or if the terminal side lies on coordinate axis, theta is said a quadrantal angle. Okay, so this means, for example, you have this one. This is quadrantal angle. The terminal side is a negative y-axis. Okay, so you have a lies in the quadrant or the quadrantal angle. Quadrantal angle, you have four choices. You see, quadrantal angle, it can be this one. The terminal initial side coincide, or this one, or this one, 1, 2, 3, 4. Right? There are 4 cases. They are classified by the position of the terminal side. It is along the positive x-axis, positive y-axis, negative x-axis, negative y-axis. They are quadrantal angles. I just say the position, I don't say the measure. Okay, after we place them in the standard way, or even before we place it in a standard way, we want to measure the angle. To measure the angle, we have degrees. What are the degrees? One revolution is said to have 360 degrees. Okay, one revolution has 360 degrees. And 1 degree, of course, is going to be the 1 over 360 revolutions. Okay. And then we have a right angle. A right angle has a right angle is 90 degrees, a quarter revolution. A straight angle is 180 degrees. Okay, right angle, straight angle, right angle. This is right angle, straight angle. It's a straight angle, right? Okay, so now let's see. Remember, we have a positive, negative angles. They represent the different direction of a revolution. So if we want to have, let's assume we place it in the standard position. If we want to have 45 degrees, where's the 45? So you have x-axis and you have a diagonal. This is 45. This is the counterclockwise orientation, positive. If we want negative 90 degrees, this way, it's clockwise and quarter. So it's a quadrantal angle. It's negative 90 degrees. And it's a 225 degrees. 225 degrees is, you see, it's 180 plus 45 degrees. 45 is a half of the right angle. 180 is a straight angle, so it's positive, so it's counterclockwise orientation. So it's 225. And last one. If we want 405 degrees, 405 degrees is 360 degrees plus 45 degrees. So 360 degrees is a complete revolution and plus 45. So you have something like this. So first you get one complete revolution and then you move additional quarter. You see, it's bigger than one revolution. You get one revolution with additional 45 degrees. And 405 degrees, they share the same initial side, same terminal side, but the process is different. Okay? This one, you just simply start from the initial to the terminal. This one, you go to the terminal, pass it, get a complete round, and back to the terminal. Okay, so that's the angle. And degree, even though it's hard to draw 1 degree, but degree is still too big if we want to apply it to some applications. So we have even smaller unit. So we define 1 degree to be 60 minute. Okay, one prime, it's a minute. And 1 minute is equal to 60 seconds. 60 seconds. So it's really like the clock. Clock, you have 1 hour is 60 minute. 1 minute is 60 seconds. Okay, so the unit is 60. So if you have 15 degrees 30 minutes, it is equal to 15.5 degrees, because 30 minutes is 0.5 degrees. Okay, and if you have 32.25 degrees, 32 degrees is 32 degrees. 0.25 is a quarter. 0.25 is a quarter. A quarter degrees is 15 minutes. A quarter hours is 15 minutes. In this transformation, you just consider degree as hours, and you can just translate between the hours, minute, and second. Okay. Okay. So, degree. Why do we define one revolution as a 360 degrees? And how do you get this 360? And this number does not fit our other number system. Like you measure the 1 meter, 2 meter, and 1 degree, 2 degree. These two things cannot be added. They're totally different. So in order to unify those two systems, we introduce another unit. It's called the reading. The readings. Let's check what a readings is. Readings, remember, reading is a measure of the angle. So we place the angle in the position, not stand in the position. So a central angle. A central angle is a positive angle whose vertex is at the center, is at the center of a circle. Okay, so you have a center, you have a circle, you have a center, then this is a central angle. The vertex is a center of the circle. It's a geometric stuff. Okay, so when you have this center, then you have the radius. You have the radius, and this when you swap the initial set to the terminal set, you see this point will give us an arc, a piece of arc. And we say the following thing. Remember, we say the following thing. If the arc is R, if the arc is equal to R, which is the radius of the circle, then the corresponding central angle is defined to have one reading. So what does this mean? This means, for example, if you have radius 1, then when you swap it, you measure the arc. If here radius is 1, you measure the arc. When the arc is 1, the corresponding angle is 1 radian. 1 radian, okay? Or if your radius is 3, 2, 3, okay. If your radius is 3, so you start from you start from one point, you go 3 length. This is length. If the radius has a had unit 3 meters, then this arc you have to have a 3 meters. If this is 3 centimeters, this is a 3 centimeter. Whatever, the same unit. When you have this 3, then unit is 3, then this central angle is called to have 1 radian. Okay, so this is 1 radian. And you can see that if you place it here, if you place this circle with with radius 1 here, if here is a 3 radian, and this part will be 1 radian. Sorry, if here is the length 3, this arc will have length 1 because they are proportional. The radius is 1, this radius is 3. So if the arc has radius 3, if the arc has a, how do I say it? If the radius is 1, the big radius is 3, big arc is a 3, the small arc will be 1. They are similar shapes, and they have the same proportion. So here's a 1, here's 1, here's 1. So the corresponding central angle is also has reading 1. So it doesn't matter what radius you choose. Just pick up a radius, and along the arc, along the circle, you draw the arc with the length r. The corresponding central angle will have reading 1. Okay, corresponding central angle will have reading 1. And what we know that one complete revolution the arc length is 2 pi r. Arc length is 2 pi r. Here you have r, it corresponds to 1. You have 2 pi r. The central angle is 2 pi, so it's 1 revolution. One revolution has reading 2 pi. 1 revolution has reading 2 pi. 1 revolution has degree 360. Okay, so this number does not come from some virtual stuff. It comes from the geometry. So 360, why it is 360? Okay, so that number is some new number. But here, this 2 pi is from the geometry. It has a relation to other numbers. Okay, so that's the advantage of reading. Okay, so again, what is 1 reading? 1 reading is a central angle with a corresponding arc, radius r. And with the reading, we can find the arc length. Find the length of an arc of a circle. Of a circle. Okay, so you have this angle theta. You have this arc. Uh, let's call it S. You have radius R. It's a proportional. It's a proportional. The whole reading, the whole reading of a revolution is 2 pi. So when you have S, the proportion with respect to the whole whole revolution is 2 pi r, and it corresponds to the central angle with respect to the whole revolution. 2 pi reading is 2 pi. So everything is a proportional here. So this is length proportional. This is a central angle proportional. They equal to each other because of the definition. Okay, so from here you cancel 2 pi and 2 pi, you get S is R theta. S is R theta. Okay, so this is the arc length. If you know the angle in the reading, you can find the corresponding arc length. Okay, reading times radius is arc length. Reading times radius is arc length. Okay. For example, if we have radius equal 2 meters and the central angle is 0.25 reading, you can either write reading or you just write RAD. Then what is the length of the corresponding arc? So the length of the arc is R times theta is 2 meters times 0.25 is 0.5 meters. Okay, so this is the corresponding arc length. The length of the corresponding arc. Okay. Now we have two system. One system is a degree. The other system is a reading. Okay, then degree 1 revolution 360, reading 1 revolution 2 pi. So 360 degrees has a reading 2 pi. Then for 1 degree, it will have reading 2 pi over 360 is pi over 180. So for whatever reading x, for whatever degree x corresponds to pi over 180 times x reading. For whatever reading, it is equal to 180 over pi times x degrees. Okay, so you can go forward and backward. So that's a translation between degrees and the radians. To get this formula, you can either from what I do here, or you can do the process like in the textbook. The textbook use the similar proportion, but it is more general. It is not more general. It's in a different approach. So either works. You just understand one process is enough. Okay. So proportional. 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 And in this part, remember this one is important formula. Arc length is r theta. Arc length is equal to r theta. Now let's get some commonly used radian degrees. We know that 30 degrees, if you get 30, x is a 30, pi over 180 times 30 is pi over 6. If you have a 45 degrees, you put 45 here, it's equal to pi over 4. If you have a 60 degrees, you put a 6 here, it's a pi over 3. If you have 90 degrees, you get pi over 2. Then you continue 120 degrees, 2 pi over 3. 135 degrees, 3 pi over 4. 100 what? 150 degrees, it's a 5 pi over 6. So 180 degrees is pi. 0 degrees is 0 reading. Only 0, 0 are equal to each other, but 1 0 means 0 reading. 1 0 means 0 reading. The other 0 means 0 degree. They have the same quantity, but they have different unit. They have the same quantity. That's just constants. Okay. So always keep in mind they are the correspondence. This is very useful. Sometimes we like to use a reading. Sometimes it's easy to understand with degrees. And also keep in mind, pi is a number. So this is a number system. This is in the number system. Pi is a 3.14 approximately. So for example, 90 degrees, it corresponds to pi over 2. Pi over 2 is about 1.57. Okay, so 1.57. So it's a number bigger than 1. It's a number bigger than 1. We have positive degree, then you have positive reading. We have negative degree, you will have a negative reading. Okay? And the positive and negative, they all depend on this orientation, the rotation direction. Okay, now let's talk about the area of a sector of a circle. The area of the sector of a circle. Okay, the area, you see the area totally depend on the, you have R, you swap this R, you get theta, then you have this sector, you can compute the area. You continue to swap it, If you swap more, if you have more reading, you have a bigger area, and this is a proportional. So the area is, this is a proportional. Area is proportional to the central angle, the reading of the central angle. Okay, so if you have a sector, if a sector has what? Has a central angle theta. Okay, the central angle is theta. Then theta over the revolution. This is a ratio. It is equal to the area over the area of the sector over the area of the whole revolution. The area of the whole revolution is pi r squared, right? The whole disk has an area pi r squared. So the ratio between the central angle is equal to the ratio between the area, right? And then you cancel pi from two sides, you will get the area of the sector is equal to 1/2. 1/2 comes from this 2. Pi cancelled, 2 survives. And r squared moved to the right side is r squared times theta. So this is area of sector formulas. The area is 1/2 r squared times theta. So you see here, technically we have the similar comparison. In the arc length formula, we try to compare. You see the central angle over the central angle of the revolution is the arc length over the arc length of the whole revolution. You see, we compare the revolution. It is proportional to the central angle. Here we do the similar thing. We get the ratio between the central angle and the radius. Sorry, central angle with the reading of the revolution, and it is equal to the ratio of area with a complete disk. With a complete disk. The same thing. But we're talking about the different concept. The first is about the length, arc length. The second is about the area. They are both a function, they are both proportional to the central angle. You get a bigger central angle, you get a bigger arc length. You get a smaller central angle, you have a smaller sector. Okay? Okay, now let's see if, example, if we know the radius equal to, for example, 2 feet, the central angle is 30 degrees. Be careful, we need reading. We can never use degrees in the computation of either arc length or the area of sector. So in this computation, we have to write 30 degrees as pi over 6. We must do this. Then the area of the sector is 1/2 r squared times theta. 1/2 r is 2. 2 squared is 4, and theta is pi over 6. So 4 pi over 12 is pi over 3. This is the area. In the exam, partial or final, this is a final answer. Don't ever divide 3.14 by 3. That's not correct. Pi is pi. Pi, we only say it's approximately 3.14. It's never equal to 3.14. Okay? So here you have to write it as pi over 3 in pre-calculus and calculus. Okay? Okay. The next, there's something called the angular speed and the linear speed. What does this mean? Assume you have a rope. You hold one end of the rope and you tie a stone at the other end of the rope. This one is fixed, and you spin this, and this is a stone. Then this stone has a trace a circle, right? You rotate it, you will have a circle. And assume initially the stone is here. After t seconds, the stone is here. T whatever time unit. After t time unit, the stone is here. Then you see here, the stone passes s distance. The stone passes s distance. This is t equal to 0. This is the time is initial time. After t time unit, the stone moves here, and then it passes certain distance s, and s has a corresponding central angle. Okay, so if you use distance over time, it passes a distance s over the corresponding time. This is called the linear speed. The linear speed, because you use a distance over time. Okay, the arc length over time is defined to be the linear speed. And because during this t units, the angle is from 0, angle changes from 0 to omega. So theta. From 0 to theta, the angle changes. So the angle over t, we use omega, and this is defined to be the angular speed. It's defined to be the angular speed. So the change of the angle over the time is angular speed. The change of the distance over time is linear speed. So we have two speeds. One is linear, one is angular. And because S is equal to r theta, so the same S, same theta. S is equal to r theta. So let's check this V. V is r theta over t. Remember, this r is a fixed. R is a radius. It does not change. So it's r times theta over t. Theta over t is omega. So there's a relation between the angular speed and the linear speed. The linear speed is r times angular speed. Linear speed is equal to radius times angular speed. Okay, so basically you actually have the same feeling. If you rotate or spin this stone, if you have a longer rope, when you have the fixed angular speed, for example, you have a 200 round per minute, something like this. If the rope is longer, the stone will travel more distance, longer distance, right? If the rope is shorter, the stone will travel shorter distance. So that fits our observation. The speed, the linear speed is proportional to the angular speed with a coefficient r. So linear speed is r times angular speed. And in this part, in whatever computation, whenever you combine the angle with other unit or with other distance or stuff, you have to use a radian. You cannot use degrees. Okay, so for example, let's see this. A child is spinning a rock at the end of a 2 feet long rope at the rate of 180 revolutions per minute. This means round per minute, RPM. Find the linear speed of the rock. When it is released. Okay, so let's draw it. Let's first draw it and understand. The rope is 2 feet long, and a stone is attached at the moving end, and you spin the child to spin this rope. And we need, okay, when the rock is released, whenever the rock is released, the rock will move in this tangent direction, and it actually has the original linear speed. Okay, once it is released, you do not hold it, so it does not move along the circle. It will move along the straight direction, and the straight direction is a linear direction, a linear speed. The straight speed is a linear speed. So we are looking for the linear speed of the stone, of the rock. The linear speed is related to the angular speed. The linear speed is related to the angular speed. It has a r omega. R is 2 feet, so r is 2. Omega, what is omega? Omega, you see here, 180 revolution per minute. One revolution, 2 pi radian. So 180 revolutions per minute. It is equal to 180 times 2 pi. One revolution is 2 pi. 180 revolution is 180 times 2 pi per minute. It is equal to 360 pi radian per minute. So this is the omega. You already have per minute, so this is a speed. Okay, so once you get this speed, you plug in, you get the linear speed is equal to 2 times 360 pi. This is the feet. It is equal to 720 pi feet per minute. Feet per minute. And in the exam, you just leave it like this. Just leave it like this. Don't transform it. Okay? So feet per minute, it's if we want to understand how fast it is, it's approximately. This is just the job in the real life. We don't actually We don't actually do it in the exam. I'm always emphasize in the exam, you don't simplify, you don't approximate. So it's about 2,262 feet per minute. For me, I have no idea about the what this speed is. Let's see. 2262 feet. Okay, so it's for me. I feel it's like 689. Oh, it's about 690 meters. Sorry, meters per minute. Divided by 7. No. Okay. Yeah. So it's very very fast. 1 minute you run 600 690 meters. It's even faster than the human being's sprint. The fast person. The first person, it's like 10 second. It's slower than it, right? Okay. Anyway, sorry. Anyway, it's very fast, so it's very dangerous. It's very dangerous to spin a rope. Spin the rope with a rock attached. Very very dangerous. We have to stop the kids playing that. Okay, so this is the measure of the angle. The measure of angle has two systems. One is the degree, the other one is the radian. Degree is an isolate system. You can only discuss the degree when you just consider the angle. Don't consider the length of the arc. Don't consider the area of the sector. If you want to combine the angle with the length with the area, you must use a radian. Okay, radian is like the bridge between the angle with other unit. And what is a radian? Radian is measured by the arc. Okay. Radian is measured by the arc. In the formula, we learn this way: S is equal to r theta. Actually, theta is also equal to the arc over the radius. Theta is arc over the radius. This is also one of a proper definition for the radian. So when you get the arc, the length of the arc, you divide it by the radius, it is equal to the radian of the central angle. When we talk about the central angle, we don't need to place it in the standard position. It's not useful. It's not necessary. Okay? So this radian is used and must be used when you connect it angle with arc length with arc length, area of sectors, and the linear speed and the angular speed. Whenever you want to relate to other quantity, you have to use radian. If you just isolated studied angle, you can use degrees. Okay, so that's not a problem. Okay, so we finish this section 7.1. If you consider them too scattered, just read the textbook and try to memorize all these concepts. They are very very important. Okay, we stop this video and start another one. Thank you.